Uh,
Recording.
okay, so I start again. Yeah, so I first want to congratulate Professor Limaco for this very nice idea to have this seminar in PD and applied mathematics. This is very interesting, and I have listened to many conferences given in these seminars. And they are all very interesting. So the subject of my talk will be about the boundary stabilization of 1D hyperbolic systems. And the outline is there. I will first present some 1D hyperbolic system. Then I will speak about 1D hyperbolic system without source terms. And then I will turn to the case where there are source terms, which a case which is a little more complicated. And then I will speak about maybe stabilization in optimal time. And if I have enough time, about viscosity and robustness. So let me start by giving some example of 1D hyperbolic systems. So the 1D hyperbolic system on which I have worked a lot is the case of the river. This is the river La Sambre in Belgium. And here is a map of this river. And you see there are some numbers, 1, 2, 3, 4, and so on. And this is a place where there are the gates. And at the gates, we are going to implement some control in order to stabilize the system. So now we are going to speak about the modelization. So there are the pools. This is what is between two gates. And we are going to denote by h of t and x, the height of the water at time t and the position x. And v is the horizontal velocity. And it is assumed that the horizontal velocity is the same on the vertical line. On each vertical line, it's the same. This is a modelization which is due to Saint-Venant. Saint-Venant is here, is on the left. And the paper is Théorie du mouvement non permanent des eaux avec application aux crues des rivières et à l'introduction des marées dans leur lit. What is important is that he found this model, the PDE that we are going to see when he was 74, which is, I think, very encouraging for many of us, I think. So what is the two equations? The two equations are, the first one is a conservation of mass. You take the derivative with respect to time of the height of the water, plus the derivative with respect to h of the product h times v, which is called the flow rate, is equal to 0. And then there is a conservation of momentum. You take the derivative of the velocity, the horizontal velocity with respect to time, plus the derivative with respect to x of g times h plus v squared divided by 2, and you require that it is equal to 0. And g is a gravitational constant. So this is so we have two equations, and it's also used, in fact, to model irrigation channels. So you can write it in a more compact form. You consider y, which has two components, h and v, and you write the equations, the two equations, as 2 yt, the derivative of y with respect to time, plus a of y yx is equal to 0. And a of y is a matrix, a square matrix, 2 by 2 matrix, and the components are v, h, gv. And if you compute the eigenvalue of a, you see that there are two eigenvalues which are given by 5. And we are going to study the case where the flow is assumed to be subcritical, that is the v square is less than z times h. Then you have the two eigenvalues which are real. One is positive and one is negative. And when there is source term, if you consider Saint-Venant equation with slope and friction, the situation is a little more complicated. You have still yt plus a of y yx is equal to 0, but you have to add some b of y, where b is given by 2. So this will be the general framework, yt plus a of y, b of y is equal to 0. And what do you mean by hyperbolic? You mean that if you compute the eigenvalue of a of y, this is a square n times n matrix, you assume that the eigenvalues are all real and distinct, and none of these eigenvalues is equal to 0. So this is the general framework. And in real life, there are many equations, there are many physical systems which can be modeled by this type of equation. Let me give you the first one, which is the transmission line. And in this case, you have two components, that is y is in R2, and the first component is the voltage, and the second component, the first component is the current, and the second component is the voltage. And this is a linear system in this case, yt plus ayx plus by is equal to 0, where a and b are given by 3. So if you consider the matrix A, which is important for us, B is the source term, but in order to see if this is hyperbolic, we look to A and we compute the eigenvalue. And you have two real eigenvalue. One is positive, the other one is negative. Another example, this is a shower. So it's a case where the dimension of the y now is 3. You have what is called the piezometric head, which is a length, which is homogeneous to a length. Then you have the velocity of the water, and T is the temperature. And it takes, again, the form yt plus a of yx plus b of y is equal to 0, where a of y, which is the matrix that we are interested in, is given by 2. And if you compute the eigenvalue of a of y, you see that they are all real. One is v plus c, and c is the velocity of the sound inside the water, so v is very small compared to c, in fact. Lambda 1 is positive, lambda 2 is v also, and lambda 3 minus lambda 3, because it's negative, is v minus c, where you see v minus c is negative because c is much larger than v. Another example, there is the road traffic, and it can be modeled by there are many possibilities, but one which is very classical is Rowe-Raskel model, which was found in 2000. Then you have again yt plus a of yx plus b of y is equal to 0. Y has two components, rho and v. Rho is the density of the car, v is the velocity of the car, and a of y is this matrix which is given in the equation 2. And if you compute the eigenvalue of a of y, you find the two eigenvalue. And now the sign is not always the same. It depends of the type of traffic that you have. If the traffic is fluid, then the velocity, the lambda 1 and lambda 2 are positive. And if the traffic is congested, lambda 1 is positive, but lambda 2 is negative. P of rho, and as a V0 of rho, you can determine this function experimentally. For example, for V0 of rho, there was some experiment which was done in Belgium, and you have this function V0 of rho, which was determined experimentally. The heat exchangers, so we have this picture. You have some exchange of heat between two fluids. And so it's like the shower, so except that you have to multiply the dimension by 2. And you have now, the system is of dimension 6. So y has a 6 component, and the PD is given by 1. And if you compute what is a of y, and compute then the eigenvalue of a of y, you find the eigenvalue which are given by 2. So then you have 4 eigenvalues which are positive, and 2 which are negative, but they are real. So there are many other examples. For example, the gas pipes, the chromatography also can be modeled by this type of system, yt plus a of yx plus b of y equals 0. The musical wind instruments, and then you see this is a case where you move the length of the interval. And you can find more examples in this book that I wrote with George Pastin 2016. And now we move to what happened on the boundary. The boundary is a place where we are going to put the control. And here, this is a picture on the river Lassan. And the picture is interesting because on the right, you see the gate is under repair. And you see what is going to be the control for this type of gate is the motion of the top of the gate, which is called the lip. So this is what is called overflow gates. The control U is the motion of the top of the gates. But you can also have this picture on the left, where now the flow is going below the gates. But again, U is the control. So in some sense, you can consider that what is the control is the flow rate, Q. And you may have the river which is much larger than the river La Sambre. This is the case of the river La Meuse, also in Belgium. And you have also some gates which are presented here. For the road traffic, you may have also what is called the ramp metering. That is, you have a light, the red and green light, and you put red and green depending on something, which is the outflow rate of the cars. So now we are going to move to what is the issue, what is the problem of stabilization. So we have this general picture, and we are going to consider the case where there is no source term, b of y is equal to 0. So we have this equation yt plus a of y yx is equal to 0. And we are going to study what happens when we are close to 0. So a of 0 is assumed that maybe after some change of variable, because the eigenvalues are all distinct and real, you can put it in this form, diagonal of lambda 1, lambda n, and you have k eigenvalue, a k lambda I which are positive, and n minus k which are negative. And you assume that the lambda I are distinct from the lambda j. And small lambda I now is the absolute value of the lambda I. Now, so this is the equation. Now we have the boundary condition. This is the condition 1. You say what is going inside the domain. For example, if you are on the left-hand side, you have to consider the component which has a positive velocity because you want to enter into the domain. So this is y plus of t and 0. If you have on the right-hand side, what is going inside the domain, inside 0, 1, is in fact the component which have a negative velocity. So it takes a form given by 1. What is going inside the domain is a function of what is going outside the domain. And the map G is assumed to vanishes at 0. And you see part of G is given by the physics, as we are going to see, but part of G, you can choose it. This is the part that you choose is called the feedback. You can choose some component of G, not all, but some component of G. You can choose them. And the question is what you want to do is to choose this component of G in such a way that you have exponential stability, at least locally. So what do you mean by exponential stability locally? So you have some Banach space in which the Cauchy problem is well posed. So you have yt plus a of y yx is equal to 0, the initial data plus the boundary condition. And you require the property 2 that the yt at the y at time t, the norm of this function is less than c times exponential minus nu t, the norm of the initial data. At least, because this is a local result, at least if the norm of y0 is small enough. And for the space, there are many possibilities. We are going to consider the case where the solution is regular. That is, x will be either ck, where k is at least equal to 1, because in this space, we know that it's well posed. In C0, it's not well posed, but in ck, it's well posed for k at least equal to 1. And there is also the case of the Sobolev space, hk, that is the function, the derivative up to the order k r square integrable. And then it's well posed for k at least equal to 2. For k equal 1, for h1, it's not well posed. And the question is, under which condition you have this property? You want to understand when you have this exponential decay. And we start with the simplest case. The simplest case is a case where you are in dimension 1, and we have something which is linear. And for example, we assume that the velocity, we have only one velocity, is positive. So this is yt plus lambda yx is equal to 0, and yt0 is k times yt1. And then you can compute explicitly the solution, because we know that on the blue line, y is constant, and the value between what happened at x equal to 0 and x is equal to 1 is given by yt0 is equal to kyt1. And then you get the property 3, which tells you that y at time tn 0 is k to the power n minus 1 yt1 0. So you have exponential stability if and only if the absolute value of k is less than 1. Now we move to the dimension 2, and for some, even in fact for the dimension n, and for simplicity, we are going to assume that the lambda I are positive, and we consider the case of a linear systems. So it takes the form yt plus lambda yx is equal to 0, yt0 is equal to k times yt1. And if you look to the exponential stability, there is a criteria which is working in this case. You look to the eigenvalue of the operator lambda yx, with the boundary condition y0 is equal to ky1. So you look to the spectrum. Of course, we know that for PDE, the fact that the spectrum is good is not always sufficient. It is necessary for the exponential stability. It's not always sufficient, but this is a case where this is indeed necessary and sufficient. And what is on the left-hand side of the implication 3 just means that you have an eigenvalue. Z is an eigenvalue of the operator lambda yx with the boundary condition y0 is equal to ky1. So you require that the eigenvalue of the operator have a negative real part and uniformly. And then you have exponential stability if and only if this property 3 is satisfied. Now we have to understand that why do we want exponential stability or asymptotic stability? This is in order to have robustness, because in practice we know that there are some errors, and we want to get that if the errors are small, maybe we do not get the conversion to 0, but we are going to stay close to 0 even if we start not so close to 0. And we want to study this robustness. So let me study a simplest case. Lambda 1 is equal to 1, lambda 2 is equal to 2. The inverse of the lambda I are denoted tau I. So tau 1 is equal to 1 and tau 2 is equal to 2, 1 divided by 2, sorry. And the matrix, which gives you the boundary condition, is given by 1, where A is a real number. You can compute, you can look to the previous criteria. You check these conditions 3. You can compute the eigenvalues. And you see that the exponential stability is equivalent to the property that A is between -1 and 1 divided by 2. Now you perturb a little bit the system. If you perturb a little bit Ka, there is no problem. But if you perturb a little bit the velocity, then there is a problem. Because if you consider this velocity, lambda 1 is equal to 4 times n divided by 4 times n plus 1. Lambda 2 is 4 times n divided by 2 times n plus 1. As n is going to infinity, lambda 1 is converging to 1, and lambda 2 is converging to 2, which are the previous value. But now, if you consider any n, y1 and y2, which is given by 3, is a solution of the yt plus lambda yx is equal to 0, with the boundary condition yt0 is equal to k minus 1 divided by 2 yt1. And you see, minus 1 divided by 2 is very far from the boundary of the interval. It's not minus 1, it's not 1 divided by 2. So you see there is a problem because you lose the exponential stability. And if C maybe is small, we do not get any convergence to zero. So we get something which is very bad. So you see small perturbation of the velocity destroys the exponential stability. This is something which cannot happen in finite dimension. In finite dimension, if you have y dot is equal to ay, if the eigenvalue of a have a real part which is less than minus delta, if you perturb a little bit, you still have exponential stability. So this is very bad news, but then people have tried to understand under which condition you have the exponential stability, which is robust with respect to small perturbation on the eye. And this is given by Sivkovsky in 1993. He defined this number rho bar of k, which is the maximum of rho. You take the diagonal matrix I theta 1, I theta n k, where theta 1 and theta n are real numbers, and rho of a matrix is the spectral radius of this matrix. And then you compute rho bar of k, and you have exponential stability which is robust to small perturbation on the lambda I, if and only if rho bar of k is less than 1. And you see there is something which is very interesting. Now the condition does not depend on the tau I, does not depend on the lambda I. So you have required that you have exponential stability which is robust with respect to small perturbation on the lambda I, but in fact you have the robustness with respect to every perturbation on the lambda I. So if we go back to the previous example, you can compute rho bar of k, and you get that this is 2 times the absolute value of a. So the condition to have something which is exponential stable and robust with respect to small perturbation is not that a is between -1 and 1 divided by 2, but it is that a is between -1 divided by 2 and 1 divided by 2. And the case, you remember, before we have taken a equal -1 divided by 2, which is not in this open interval, and then that was not robust. Now we move to the nonlinear case. In order to handle the nonlinear case, we define this norm, the P norm of vectors, which is the classical one, the infinity norm. And associated to this norm, you have the P norm of a matrix, as usual. And then you define rho P of k, which is the infimum of the norm, the P norm of delta k, delta -1, where delta describes the set of diagonal matrices with positive entries on the diagonal. So this is some number which depends on k. K is going to be g prime of 0 because we are going to linearize the system. And so the condition will be on g prime of 0. And then there is this very nice result due to the Chinese school, in particular Professor Li Tatsien in 1994. They prove that if rho infinity of g prime of 0 is less than 1, then you have exponential stability for the nonlinear system. This is a very nice result, and the stability is for the CK norm, whatever is k, provided that k is at least equal to 1. And the proof relies on the use of direct estimate on the solution and their derivatives along the characteristic curves. So this is a very important result. You have this sufficient condition for exponential stability for the CK norm. And now, of course, we want to compare rho bar of k and rho infinity of k. You cannot expect to do better than the linear case. So you have rho bar of k, which is less or equal than rho infinity of k. But unfortunately, there are examples where this inequality is strict. That is, for example, if you consider this matrix Ka, which is defined on the slide, you can compute rho bar of Ka. This is square root of 2 times A, and while rho infinity of Ka is 2 times A. So for the linear system, the condition is A is less than 1 divided by square root of 2. And for the nonlinear system, you get a stronger sufficient condition, which is that A is less than 1 divided by 2. So the question is that Is this sufficient condition? Can we improve this sufficient condition by requiring that rho bar of G prime of 0 less than 1, which is a weaker condition? Before giving some result on this, let me point out that it's also possible to consider the Sobolev spaces. This is what I did with Georges Bastin and Brigitte d'Andrea Novel. We have another condition, which is rho 2 of G prime of 0. If rho 2 of G prime of 0 is less than 1, then you have exponential stability for the hk norm, whatever is k, at least if k is at least equal to 2. For h1, we know it's not well posed, but for k larger than 1, it's well posed. And then we have another condition, which is rho 2 G prime of 0. You have to compare this condition, but let me before mention that you have also some estimate on the decay rate, which is optimal, in fact. You consider this nu, which is in this interval. You see the 0, and then the number which is given after is strictly positive because rho 2 of G prime of 0 is less than 1. Then you have the decay rate, which is given by 3. Now we want to compare rho bar and rho 2. And now the situation is little better because you have equality between rho bar of k, which is the optimal result for the linear case, and rho 2 of k. You have equality until the dimension 5. And for the dimension larger than 5, then this is not true. You have cases where the inequality is strict. But in the case of the river Lassan, of course, you have 8 gates, so the dimension is 16. But this is block, you have a block structure, and the size of the block is 2, which is less than 5, less than 6. And so it's still working when you have a block structure of K. And if you compare rho 2 of K and rho infinity of K, this is a sufficient condition for the exponential stability for the CK norm. Then you have rho 2 of K is always less or equal than rho infinity of K. So our sufficient condition is weaker. And you have cases where the inequality is strict. But now the question is, does rho 2 of G prime of 0, which is sufficient for the exponential stability for the HK norm, is it sufficient for the exponential stability for the C1 norm, for example? It turns out to be false, in fact. With Oaimin and Nguyen in 2014, we produced an example where you have rho bar of K, which is rho 2 of K because we are in dimension 2, less than 1. So you have the exponential stability in the HK norm, in the Sobolev spaces, while rho bar of K is a little larger than 1, but you do not have exponential stability for the CK norm. So this is something which may be surprising. The exponential stability depends on the Banach space that you consider. Let me give some insight on the proof for the case of the H2 norm. So we consider first the case where you have a linear system. So we define the Lyapunov function, which is given by 1. Q is a matrix that we are going to choose later on. You compute V dot, you do integration by parts, and you get that if rho 2 of K is less than 1, you can choose Q in such a way that the boundary term is positive. So this is minus the boundary term. So minus the boundary term is negative. And so you get that V dot is less or equal than minus mu V. And the mu is important because if you do not put mu, you cannot expect to have a strict inequality. You will get that V dot is less or equal than 0. Of course, when you are in finite dimension, if you have V dot less or equal than 0, you try to use the LaSalle invariance principle. But in this case, when you are in infinite dimension, you have to, in order to use the LaSalle invariance principle, you have first to prove the free compactness of the trajectory, which might be difficult. So it's better to introduce this mu in order to have a strict Lyapunov function. Now, if we try to consider the nonlinear case, if you do the same for the nonlinear case, and there are two new terms, n1 and n2, which are in some sense cubic, at least cubic. So if we were in finite dimensions and the cubic term, you can absorb it in the quadratic term when you are close to zero, but there are more derivative in this cubic term than in the quadratic term. So you cannot bound this cubic term by the boundary, by the quadratic term. So you have to be a little more careful. In order to deal with n1, you are going to assume that choose q, which depends on y, in order to have the commutation. You have this commutation, a of y, q of y is equal to q of y, a of y, and q of 0 is given by 1. And in this case, n1 is going to disappear. But you still have the problem with n2. And n2 is a cubic term, but there is a derivative inside this term, and this is a problem. And in order to handle this problem, you have to keep going. That is, you have to do the same for the first derivative and the second derivative. So we consider v2, v3, where a of y and s of y are going to commute with a of y again and satisfy some property at 0. And then you get that v dot is less than or equals I minus alpha v, and you can get some estimate on alpha. And this gives you the exponential stability with the estimate on alpha, in fact. And so we have applied this to the river La Sambre and also to the river La Meuse, and you have produced at each gate a feedback which allows you to get some exponential, this exponential decay rate, and that is working very well. Now we move to the case where there is a source term. So there is this b of y. You remember there was this b of y. So yt plus a of y, yx plus b of y is equal to 0. Again, where is the control? The control is on the boundary. You assume that what is going inside the domain is a function of what is going outside. And you assume also that now you have some equilibrium. The equilibrium now maybe is not equal to 0 because it can depend on x now. So you cannot assume that this is equal to 0. Now the equilibrium around which we are going to study the stabilization may depend on x. So, but we start again maybe by linearizing the system around y star, and we have this equation if we are in dimension 1, n is equal to 1. You have this simple equation, and then you have this boundary condition, yt0 is equal to u of t, and you have to choose u of t in order to get exponential stability, first for the linear system and then for the nonlinear system. And in this case, this is very simple. You just take q equals 0, and this solves the problem. You will get the exponential stability. You can compute explicitly the solution, in fact. Now we move to the case of dimension 2. Now we are going to assume that one velocity is positive, lambda 1 of x is positive, and the other velocity is minus lambda 2 of x. It's negative because lambda 2 of x is assumed to be positive. And you assume that on the left-hand side, while you have no control, this is the part of G which is fixed. y1 t0 is q, y2 t0, this is fixed by the physics. And on the right-hand side, you have to choose what is y2 t1, and this uses it to be u of t. This is u of t, and you choose u of t, which depends on maybe some value. So in order to explain the result, we first perform a little change of variable in such a way that now you see, for the source term, there is no diagonal term. You see, for the first line, the source term is a of y2 tilde. There is no y1 tilde. And for the second line, for the source term, there is no y2 tilde. And then you try to stabilize this by using a linear feedback as we have done before. So you take u of t is equal to k times y1 t1. And if you take C equals 0, then there is no problem. You can just take K equals 0, or even the absolute value of K less than 1, and then you get the exponential stability. And now the question is what happened with the C? And with the C, there is a new problem. That is, if C is at least equal to pi, whatever you do with K, it's not going to give you exponential stability. It will be always exponentially unstable. So you cannot use this simple feedback. You have to do something different. And what you are going to do is what is called backstepping. So the backstepping in finite dimension, this is related to the problem of stabilization of this system. X dot is equal to f of x and u, y dot is equal to x dot is equal to f of x and y dot is equal to u, and you want to stabilize the system. And the idea is that to stabilize the system, in some sense, it is sufficient to stabilize x dot is equal to f of x and y, where the state now is not x and y, it's just x, and the feedback, the control is y. If you can stabilize this system, often you can stabilize the larger system. X dot is equal to f of x and y dot is equal to u. And there is some application to PD, but what is very important for us is the generalization of this type of method for the heat equation, that you try to consider some heat equation, you do some discretization, you have a system for which you can use this backstepping approach, and then you go back, the mesh of the discretization is going to 0, and then you see that it's equivalent to try to transform the PDE into another one by a transformation of the second kind, a Volterra transformation of the second kind, and I'm going to show you that on our system. But for the survey of this method, which is due essentially to Miroslav Kristik, there is a nice book by Kristik and Shmilayev. So let's try to do it in our situation. So we have the y tilde system that we want to stabilize by using some u of t, which is well chosen. And we are going to try to transform the first system into the second one, which is the second one. Now it's easy to stabilize it because you can just take capital U of t is equal to 0. So now is it possible to transform the first system into the second one by using a Volterra transformation of the second kind? The interest of the Volterra transformation of the second kind is that this transformation is always invertible. So you take this capital Y, which is given by this formula, and you want to transform the y tilde system into the capital Y system. And you see that it is possible if P, if and only if, P satisfies R1, R2, and R3 is equal to 0. So the PDE part, which is 4, you see it's an hyperbolic equation. It is an hyperbolic equation, and you have some boundary condition, which is given by 2 and 3. But it's not given on some rectangle, it's given on some triangle. So you have an hyperbolic system on a triangle. But still, you can prove that at least this Q is not 0. If Q is not 0, so this is the generic case, so let's forget the case Q equals 0. You can make it. If Q is not 0, you can transform the first system into the second one. If Q equals 0, it's not possible. But if Q is 0, you have to transform the first system, the y tilde system, into the system 2, where you see there is this new g of x, y2 t0. Then it's possible you can do that. But then you have to be careful. The feedback capital U is equal to 0. You can transform into small u. And if you compute small u, you get 1. That is now u, the small u, the feedback, does not depend only on the value of y1 and y2 at the boundary, but it depends on the value of y1 and y2 on the full interval. But you can construct an observer. You can try, because of course it's difficult to measure y1 and y2 at any point between 0 and 1. But you can construct an observer, which is this. You have this, you start with the system 1, you measure only y1, t1, and you try to understand, to get some estimates on y at any point x. And for that, you construct an observer which is given by 2. Y1 at is going to be some approximation of y1 if the time is large enough. Y2 at is going to be an approximation of y2 if the time is large enough. And how do you choose? So you see there is the gain of the observer, which is B1 and P2 that we are going to choose. And we are going to choose again in order that if we consider.
That's okay.
So I just finished with that. So it's possible to construct this observer, and then everything is working well, at least for the linearized system. And then if you want to study the nonlinear system, it's more complicated. You have to, there is some cases where it's not so easy to get the result, but in this case where you measure at x equal 1, it's working. But if you measure at x equals 0, then there is some problem sometimes. So maybe I'm going to stop here, and thank you very much for your attention, and I apologize for this problem of the connection. Sorry.
No, it's okay. So thank you, Jean-Michel, for this wonderful talk. And we have time for a couple of questions. So, okay. So if not, thank you again, Jean-Michel, for your talk.
Oh, thank you. Thanks for the invitation. It was a pleasure to give this talk. So I stopped.